Well, today I'll just be introducing you guys to machine learning, and credit to some of the AI AI officers for a few of the slides. And we meet on Friday, so if this stuff interests you, you guys can check us out on Friday. Okay, first of all, what machine learning is. So let's define it. So machine learning, AI and deep learning, they're all used interchangeably, kind of, but they're different things. So machine learning is a subset of artificial intelligence. Artificial intelligence is just a technique which enables machines to mimic human behavior. But machine learning uses statistical methods to enable machine to improve with experience. So it's AI and then ML and then deep learning inside. Deep learning is the use of neural networks, which you may have heard of. Now, really quickly on the machine learning definition. So you could say a computer program is said to learn from experience E with respect to some task T and some performance measure P. If this performance on T as measured by P improves with experience E. So let's break that down. For example, if you have an email spam classifier, just classifying if emails are spam or not, the task T, so it's task T, is classifying those emails as spam or not spam. And it's supposed to learn from experience E by watching you label emails as spam or not spam. And its performance is going to be the number or the fraction of emails it correctly classifies. So it learns if its performance improves as with experience E, and that's measured by P. That's all machine learning really is. And really quickly on the techniques. So there's supervised learning and there's unsupervised learning. In supervised learning, you're given the correct answers and you kind of your goal is to develop like the best predictive model, while in unsupervised learning, you're kind of grouping and interpreting data. So here we have unsupervised learning, where you're making groups out of you're trying to find patterns in your data, and here's clustering. And over here in supervised learning, you're trying to find a way to predict. So if it's on this side of the line, you predict the best line. And then if it's on this side of the line, you can predict one thing. And if it's on the other side, you can predict another thing. And so here's another example of supervised learning. Your goal is to predict, is it a duck or not a duck? Over here, you're grouping stuff. So there's not really any correct answers you're learning from, but you can still recognize patterns in your data. Now let's talk about deep learning really quickly. First of all, machine learning is, contrary to popular belief, it's really not a new idea. Sorry, it should be deep learning. It's not a new idea, and it's taken off recently, but it's certainly not a new idea. So Frank Rosenblatt in 1958 came up with the perceptron. And the only reason it didn't take off earlier is because we didn't have enough data and we didn't have enough computation power. Now we have both of those, so that's why deep learning is so successful. So the perceptron really quickly is just in a neural network, it's a single neuron. You feed it inputs x1, x2, and so on. Here's x1, x2, x3. It has weights. So each of these lines are weights. So you multiply, you multiply x1 by this weight, you multiply x2 by this weight, and you multiply x3 by this weight. And then you add them together and you get an output. And that output, you have a threshold. So if that number is larger than the threshold, then it's 1. So it's like true or false, right? And you can imagine your goal is simply to learn what are the best weights so that this thing does well, this perceptron does well on whatever task it has. It has to learn the correct weights so that when you multiply them and add them together, you get the outputs that you want.
Very unrelated but fun, I guess, is does anybody know like the biological terms for the different parts of the neuron? Like the parts coming, the inputs and the outputs. Does anybody know? Like why does this represent a neuron? Like what's similar about it? Anybody? Nobody here does bio? That's so sad. Am I the only one? Come on, I know some of you guys do. Okay, well, anyways, it's basically like a neuron, right? Because basically in your brain, right, like neurons take in a bunch of different inputs from other neurons through synapses, right? And those go into the dendrites, which are your inputs over here. and then your neurons send it off to another neuron using axons. And the reason why this is useful, right, is because you can learn things through the different pathways in your brain. So essentially, the idea behind these kind of things for computers is that they could also have these really complex functions to actually learn things in ways that humans can't program them to do, right? So that's the basic intuition behind these neural networks.
Yep. And going back to before, deep learning is a subset of machine learning. And it's just these perceptrons stacked together. So there's many perceptrons. You can, so yeah, you're stacking neurons together. And again, they're inspired by brain neurons. And the idea is that certain inputs will fire certain neurons here, and certain neurons firing here will trigger another certain set of neurons to fire here. And again, like Rohan said, you're sort of learning like a pathway, and you'll get your output based on those the correct things firing. And your goal is to learn the correct weights. There's several different types. There's RNNs, CNNs, etc. And there's a concept of universality, which is just a neural network can learn any function to an arbitrary degree of accuracy. So that's pretty cool. And this is essentially why deep learning is so good. Neural networks, like other traditional machine learning methods, they kind of just level off at they hit like a plateau, but neural networks are able to, again, model to an arbitrary degree of accuracy. And yeah, here it is again. Here are two, I'll be posting the slides later so you can view the details. Here are two good resources. But again, you can treat each neuron as a function that takes in inputs from the previous neurons. And the idea is, again, certain neurons firing here will cause these neurons to fire here, which will cause these neurons to fire here. And this combination causes this to fire, which if we're, in this example, we're taking in a picture of a handwritten digit. We're trying to figure out which digit it is. So if I write a 0, it should fire 0. And these are the 784 pixels. These pixels cause something here to fire and cause a certain set of neurons here to fire. And then this causes 9 to fire, or to fire the most. Again, key idea, learn the best weights, learn the best things to multiply them by, still the correct things fire, and the model's outputs are as correct as possible. Now let's talk about the various machine learning domains. So computer vision, NLP, reinforcement learning. If you've heard these things, I'll just break down those things into more detail. First, we'll do computer vision. So object detection, segmentation. Start off. Okay. So computer vision is an overarching field that relates to all models that act on images or videos. And they can use a variety of models. And it's probably one of the, if not the most prominent field of deep learning, because people find computer vision pretty cool. You can see like face identification and whatnot. Self-driving cars, medical image analysis, manufacturing defect reduction. All these things are examples of applications. Now, classification is pretty straightforward. It's just classifying image into one of the predefined categories. And it generally uses something called a convolutional neural network. And I think we'll be demoing that in a future meeting. And there are benefits to convolutional neural networks. And these are the benefits, but I think we'll leave that for a future meeting. Localization. So you're not only classifying the object, but you also want to find the position of the object with the bounding box. And you'll find that with typically 4 things: an X and Y coordinate of the top left corner, and a width and height. And that will give you all you need to know for the bounding box. Object detection. So this is localization and classification multiple times per image. And there's a variable number of objects. So it's not just one object in an image. And this is typically done through methods like YOLO or NMS. YOLO with NMS. And you'll basically be having these boxes slide through and identifying which boxes are most likely to contain an object. And then after you identify these boxes, then you can classify. Computer vision, segmentation. Okay, segmentation is you're creating a mask for the object. So it's not just a bounding box. This is clearly useful for anything such as, especially for medical applications. And even my Zoom background right now, this is segmentation. So like I bring something in. Zoom is trying to find out where I am, and then it's blurring my background. It's also used in self-driving cars, and it essentially just has extremely diverse applications. Here's an example of trying to find a brain tumor, and this is using segmentation. And this is the, again, in supervised learning, you have the correct one up here, and then you have the predicted one down here. So you can see it's pretty close. Four things together, this basically sums up the main things of computer vision. There's one more thing, which is, identification. And identification is just given a specific object, you're trying to find instances of that object. So you can find, like when you have one picture. So this is a good example of one-shot learning, where you're given like one, you won't, usually when you have training data, you have lots of training data. But here you have one, you have to learn this from one person. So you're given one face, and you're supposed to identify that in one or a few faces, and you're supposed to identify that face in all future cases. So that's called one-shot learning. You don't have millions of pictures of one person and trying to find that same person. And this can be done through like Siamese networks, where you just have two identical networks and you're encoding each face, and then you can compare the encodings. So here are generative models, which are really interesting. There's autoregressive, which is you're just guessing, you're using like a language model. Well, a language model is guessing the next word in a sentence. So given what I've said in the sentence so far, we're guessing the next word in the sentence. But in autoregressive, the token now becomes a pixel. So the token's a pixel instead of a word. And now, given each pixel, you're trying to guess the next pixel. You're trying to guess it in a likely way, so you can generate images this way. Variational autoencoders. Here's a great video explaining it. You guys can check it out later. And the idea really is just you're compressing an input into this latent space representation, and then you're decompressing it. But when you're in this latent space, you can modify the latent variables and get new outputs and generate stuff that way. And then there's GANs, generative adversarial networks. They're notoriously hard to train, but they produce very realistic results. The idea is you have a generator and a discriminator. The generator is generating the stuff, and the discriminator is trying to detect what's real and what's fake. And they're working against each other. So you're playing, And here's an example, which face is real. So one of these faces is generated, and you can click on the real person. And just by refreshing, again, one of these faces are generated. And one more cool thing is this person does not exist. So this is a fully generated face. This person does not exist. If I refresh, I'll get another face. Doesn't exist and doesn't exist. You can see it's really realistic. That's really cool. Now on to NLP, natural language processing, and the 10 major tasks. So models in this field are usually called language models. I brought that up before. It's just an input of 784 pixels. It's you can have long sentences, you can have short sentences, obviously. NLP, natural language processing, is just broken up into two things: natural language understanding and natural language generation. Understanding is like classification, named entity recognition. So if I give you a sentence, you're trying to locate all the names of places and names in general. Sentiment analysis, I give you a sentence, you're telling me basically the tone of the sentence. Is it a positive review? Is it a negative review? Is the person mad, right? And this brings me to the 10 main tasks of NLP, which should give you a good idea of what NLP exactly is. There's question answering, which is straightforward. Given a context, which is the background information, and a question, you have to return the answer. So if I give you a story and I ask you something about the story, it's like, where did Sally go? You're supposed to return the correct answer. Machine translation, when you use Google Translate or any other translation, you have the source language and you translate to the target language. Summarization, straightforward as well. You're trying to output a short summary of a long document. You can generate like meeting notes from this or whatever. Natural language inference is just saying, given a premise and a hypothesis, does the premise entail, contradict, or is it neutral, right? Which is one of the harder tasks because it needs like some common sense. Sentiment analysis, classify the sentiment expressed. Again, is it happy? Is it a positive review? Semantic role labeling, and given a sentence, you're supposed to label who did what to whom, when and where. That can also be hard at times. Relation extraction, you're trying to output the kind of relation given a document. Semantic parsing, you're turning the text into structured data, such as like a SQL database. And the last two are goal-oriented dialogue. So based on what the user says and the system's actions, you're trying to keep track of the goals of the user. Common sense reasoning, which is just Joan thanks Susan for the help she had given. So she had given is not necessarily clear. Who had given help? It needs some common sense reasoning because she could refer to both of these people. A common, the most common, well, it was the most common model architecture, which is just RNN. It's just a neural network that works well with sequential data. So it's great for NLP. So it's, sequential data. So you have words in a sentence. And an RNN is perfect for this because it solves problems with a standard feed-forward model. You're not learning features. You're learning features based on position in a sentence or whatnot. And you have variable input size. And you avoid the problem having too many weights because you're using the same. So instead of that big network I showed you earlier a long time ago, let's see. I can still get to it. So just an image with 28 by 28 pixels will give you 784 inputs. And you can imagine how long a sentence could be, and it's a variable input. And when you have everything in between, you have a lot of weights. That can be a big problem with not only overfitting, which is like memorizing your training data, but it's also a problem speed-wise. But RNNs solve this by using the same shared weight. And there's variations of this as well, obviously, like GRUs, long short-term memory, bidirectional RNNs. But what has killed this, and like one of the biggest changes in the field are one of the biggest discoveries, breakthroughs, are transformers. So it killed the RNN, and its application potential is massive. So it's not sequential, which means it can parallelize well on GPUs. You don't have to wait for the previous things to finish to calculate the next. You can calculate things at the same time. And it's based on this idea, this concept of attention. This is kind of beyond the scope of this presentation, but if you're interested, you can attend AI Club meetings on Friday. And one of the coolest applications of this is GPT-3, which is pretty recent. And it's like they built a text generator so good, it's like too dangerous to release. It's just really impressive. Here is a quick example. So someone used, in the first week of release, I think, someone used GPT-3 to write fake blog posts that ended up at the top of Hacker News. Hacker News has like 5 million users. It's incredibly difficult to get to the top. And someone even guessed it was GPT-3. It's like, this is either something written by GPT-3 or the human equivalent. But then the community quickly downvoted that comment saying like, hey, so nobody actually knew this was a computer writing these fake blog posts. And it really just ended up on the top. Here's another example, generate a Flask application that takes the use. It can actually write code. And here it's generating the code for your query, which is just really, really impressive. It also enables captioning. So just you can imagine video captioning. And here, you're using an image transformer here. Again, instead of using words as your tokens, like you're generating in sentences or generating essays or big blog posts, you're using pixels. And here's generating really, you can see here, it's really realistic. And it's finishing off what you started. Oh, and super resolution, of course. You can start off with these pixels here and you're generating to like very realistic. Yeah, very realistic possible outcomes. In video prediction, you have your text, and you can you generate captions and generate videos. So you can actually output video features or images to go along with text. Last thing I'll cover today is reinforcement learning. I'll go over this pretty quickly because we only have 5 minutes. Okay, basically reinforcement learning is good for sequential decision-making tasks. So the easiest way to put it is like if you're playing a video game, reinforcement learning is perfect for that. And robotics and whatnot. So you have an agent, which is inside an environment, and this agent takes actions, which are either given rewards or consequences, and it reacts to that. So this is all there is to it, really. To put it simply, an action gives a reward and a consequence, and it reacts to that. So that's how it learns. Okay, again, an agent is an entity or an object that exists in an environment and it interacts with this environment in a rational manner. So it perceives changes. So this is the main picture that sums it up. Based on the given state, it will take an action. So it takes this action and it gets a reward or consequence. And now it has a new state. And then based on this new state, it will take a new action and whatnot. So this is how they kind of learn to interact with the world rationally. And of course, based on the reward, it will learn to it will essentially learn. And a really good example of this is hide and seek. So here are hide and seek. It learns like here they learn to block the doors. But over time, they'll learn to use ramps. So red is trying to find blue. It's hide and seek. Blue learned to block the doors. But now red learns to go over the ramp. But now they learn to steal the ramp. So again, this is really fascinating things that you can learn more about. Some applications, Alphago, which is Google DeepMind's a Go playing agent. So Go is like the most challenging classical game, and search trees don't work. Like in chess, search trees work. It's not really intelligent, but in Go, it's like 10 to the power of 360 possible moves, and you can't use a search tree for that. And AlphaGo beat all the top human players. But then AlphaZero beat AlphaGo 100-0 just by playing games against itself. That's just crazy impressive. And it's using no previous information. There's no human play match data, nothing, given the rules. And for a video game, it can get, for video games, you know that OpenAI is 5. They beat the world champions in Dota 2-0. This is obviously a complex multiplayer game that requires long-term strategy and planning. They learned entirely from self-play, like no search from human replays. And it's interesting to note that it has a really different playing style from humans. And just to wrap this up, to give you the best resources to learn machine learning, if you're just starting out, 2 really good courses are Stanford Machine Learning. So this is probably the most popular online course for machine learning, and it's really good. Here's the deep learning specialization, which means there are 5 courses in it. And this too is the courses. There's 1, 2, 3, 4, 5. And this too gives you a very good introduction to machine learning. But these don't actually go through code much at all. And if you're interested in diving into the code and applications immediately, there's machinelearningmastery.com, and they give you like step-by-step tutorials with code examples. And the goal is to give you a top-down learning style. So instead of learning all the relevant math and whatnot before actually applying and building your own projects, it kind of gets you into projects as soon as possible. Now, if you're advanced or intermediate, or after you've taken, for example, after you've taken this course, David Silver's Introduction to Reinforcement Learning is very good. So it's a 10-part course. It's probably the best course in best introductory course to reinforcement learning. And here is Stanford's CS 224N, which I've actually watched through. So here you have, I think, 20 lectures. And yeah, 20 lectures. And it's really good. I believe Stanford has other machine learning courses as well. Yeah, they have other machine learning courses as well, including reinforcement learning. And I think a general machine learning course. So you can actually watch the general one before watching this one if you want to. And this is natural language processing. And that is it. If you're interested in this stuff, AI Club meets on every Friday at 1 p.m. and we are actually starting our reinforcement learning unit this Friday. And Rohan, you want to give them the meeting flag?
Oh, okay. Yeah, let me put it in the chat. But yeah, thank you guys for coming. Hold up, bro.
If you have any questions, ask.
Yeah, if you guys have any questions, feel free to ask. Okay, there you go.